Hey everyone, welcome. Today we're tackling Leetcode problem 2302, count subarrays with score less than k. It sounds a bit mathematical, but don't worry, we'll break it down nice and easy. The goal is to understand the problem and find an efficient way to solve it. Ready? Let's dive in. Alright, so here's the official problem description. The main idea is this. We're given a list of positive numbers, called, and another number. We need to find how many subarrays. Remember, those are continuous chunks of the original list. Have a special that's strictly less than, and what's the score? It's the sum of the numbers in the subarray, multiplied by the length of that subarray. So, sum times length needs to be less than k. We just need to count how many subarrays satisfy this condition. Simple enough, right? Let's walk through the first example. Our list is 2, 1, 4, 3, 5, and k is 10. We need subarrays whose score, sum times length, is less than 10. Okay, look at the single numbers first. The subarray just containing sum is 2, length is 1. Score is 2 times 1, which is 2. Less than 10. Cool, that's 1. The subarray with just score is 1 times 1, which is 1. Less than 10. Got another. Same 4 and by themselves. Their scores are 4, 3, and 5, all less than 10. So that's 5 subarrays already. Now what about longer ones? How about 2, 1? The sum is 2 plus 1, which is 3. The length is 2. Score is 3 times 2, which is 6. Still less than 10. So we count this one too. That makes 6 subarrays. What about 1, 4? Sum is 5, length 2. Score is 5 times 2, which is 10. Is 10 strictly less than 10? Nope. So we don't count this one. Any longer subarrays like 4, 3, 5 will have even bigger sums and lengths. So their scores will definitely be 10 or more. So the final answer is 6. Okay, so what's the most obvious way to approach this? Well, we could just list out every single possible subarray. Start at the first element. Make subarrays ending at the first, second, third. Then start at the second element. Make subarrays ending at the second, third, fourth, and so on. For each one, we calculate its sum, find its length, multiply them, and check if the result is less than. If it is, we add 1 to our total count. This works, but think about how many subarrays there could be. If the list has items, there are about n squared, divided by 2 subarrays. And calculating the sum each time might take up to steps as well. So this brute force way could be something like order n cubed, or maybe order n squared, if we're clever about the sum. Either way, that's probably going to be too slow if the input list is really long. We should look for a faster method. Let's try a different angle. Instead of generating all subarrays first, what if we use a sliding window approach? Imagine we have a window defined by a left pointer, let's call it, and a right pointer. This window represents the subarray nums. We can keep track of the sum of numbers inside this window as we slide it. Now let's fix the right end and see what happens. As we move to the right, making the window longer, both the sum and the length will increase, since numbers are positive. This means the score, sum times length, will also definitely increase. What if the score gets too big, meaning it becomes greater than or equal to? Well, to make the score smaller again, our only option is to shrink the window from the left side by moving the pointer to the right. This reduces the sum and the length, thus reducing the score. So the plan is this. We'll slide the right end across the array from left to right. For each we add the new number nums to our running current underscore sum. Then we check the score for the current window. J, is the current underscore sum times the window length, which is j, I plus 1, less than k. If it's not less than k, meaning it's greater or equal, our window is too big or has too large a sum. We must shrink it from the left. We do this by removing nums from the current underscore sum and moving one step to the right. We keep doing this shrinking until the score for the window finally becomes less than. Now, here's the key part. Once the window has a score less than k, how many valid subarrays does this tell us about? Think about it. If the subarray from index all the way to has a score less than, what about a shorter subarray that also ends at, say, starting at index I plus 1? Its sum will be smaller since we removed the positive number nums, and its length will be smaller. So its score, smaller sum times smaller length, will definitely be less than the score of ij, which was already less than. The same logic applies to subarrays starting at I plus 2, I plus 3, all the way up to the subarray starting and ending at j. all of these subarrays ending at j will have a score less than. How many such subarrays are there? Well, the starting positions can be I plus 1, j. Counting those gives us exactly j, I plus 1 valid subarrays. So for each position, once we've adjusted so the window ij is valid, we add ji plus 1 to our running total count. Then we move to the next position and repeat. Okay, here's the Python code implementing that sliding window logic. It might look a bit dense at first glance, but it directly follows the ideas we just discussed. We'll go through the key parts piece by piece on the next slides. Don't worry about understanding it all at once. First up, we initialize our variables. Count is what we'll return. It stores the total number of valid subarrays we find, starting at 0. Current_sum will keep track of the sum of numbers inside our current sliding window, also starting at 0. Left is the pointer for the left edge of our window, starting at index 0. And n is just the total number of elements in the input list nums. Pretty standard setup. Now the main part is a loop. The right pointer iterates through all possible indices of the array, from 0 up to n1. In each step of the loop, right represents the rightmost boundary of our current subarray candidate. The first thing we do inside the loop is expand the window to include this new element at index right. We do this by adding nums right to our current_sum. After expanding, we need to check if the current window, left-right, is valid. We calculate the score, current_sum times the length, right, left plus 1. We need to be a little careful here. The sum and length could potentially get very large, maybe causing their product to overflow standard integer types before comparing with k. A safe way is to cast the sum to a floating point number before multiplying, just to be sure. So while the score is greater than or equal to k, meaning it's not strictly less than k, we need to shrink the window. We do this by subtracting the leftmost element nums, left from the current_sum, and then incrementing the left pointer. We keep doing this while loop until the score becomes less than k. The condition left less than equals right ensures we don't move left past right. Once the while loop finishes, we know that the current window defined by left-right has a score strictly less than k. As we figured out earlier, this means all subarrays ending at right and starting anywhere from left to right are also valid. The number of such subarrays is right, left plus 1, so we add this number to our total count. This happens for every position of right. After the for loop finishes processing all possible right endpoints, the final count holds the answer, which we return. So how efficient is this sliding window approach? Let's look at the time it takes. The right pointer goes through each element of the array exactly once. The left pointer also starts at the beginning and only moves forward, never going past right. In total, each element is added to the sum once and subtracted from the sum at most once. This means the total work is proportional to the number of elements in the list, so the time complexity is big O of n, or order n. That's really efficient. And what about memory? We're only using a few variables like count, current_sum, left and right, regardless of how big the input array is. So the space complexity is constant, which we call big O of 1 foot, or order 1. Much better than our initial brute force idea. Alright, let's quickly recap. We needed to count subarrays based on a score calculated from their sum and length. The brute force approach of checking every single subarray was too slow. The efficient solution used a sliding window. We expanded the window from the right using a pointer and maintained a running sum. If the score, sum times length, became too large, greater or equal to k, we shrank the window from the left using a pointer until the score was valid again. The crucial insight was that once the window ij became valid, all j, I plus 1 subarrays ending at j were also valid. This gave us a fast, order n time and order 1 foot space solution. Hopefully that explanation made the problem in the sliding window solution much clearer. If this helped you out, I'd really appreciate it if you hit the like button. Consider subscribing for more Leetcode explanations like this one. And if you have any questions or thoughts, feel free to drop them in the comments below. If you're feeling extra supportive, you can always contribute to the Boba Fund. Thanks for watching, keep practicing, and I'll see you in the next video.